I need to be here. Okay, so log normal chord increment. All submissions should be completed. Okay. Unlike the previous lecture where we modeled the okay. First we'll discuss so-called log normal distribution. Okay. This is something to do with the description. Find the average signal strength, persistent strength. Fine. Power received will not be the same. Same over a short time span, but it does keep changing. Okay. Usually the signal average signal power, even though we fix the transmit receiver locations, the average signal power averaged over all the short term has to justify why there is a change. Usually these changes are caused by various obstructions in the path between the transmitter and the receiver. Okay, there is a transmitter, the receiver, then this received signal goes through various obstructions. Okay, so it may go through a number of buildings in between, or trees, whatever it is, there are obstructions. We're not talking about, multi-path propagation and short-term variations here. These are the long-term variations happening. Okay. So, what could possibly happen? The trees grow, there are trees in between. Characteristics of the change over seasons. Buildings do not change, but inside the buildings could possibly change, or a new building may pop up. Many things can happen for a long period. Okay. So one has to characterize these variations. It's not really easy to characterize. start to statistical calculations of signal. It will develop a model, will give the rationale for this model. Measurements indeed show that such variations are possible, and the signal statistics match with the theoretical observations. Okay, so we'll start with the first principle. Okay, there are a number of obstructions. Each obstruction has a width delta R1, delta R2. There could be buildings, trees, tunnels, whatnot. Okay, delta R3. This is just the width of the obstruction. Okay. Then each obstruction causes an attenuation alpha I. We'll talk about what this is. 1, alpha 2, alpha 3, and alpha n. Okay. Okay. Well, we have to describe what these alphas and deltas are. That EM is the electric field in free space. Okay. EM is equal to E0 raised to minus alpha plus J beta multiplied by R. Have you seen something like this when I'm implementing? Where R is the direction of propagation. Okay. Alpha is the amplitude attenuation constant. Beta is the phase attenuation constant. That's the function of the medium. The beta is the phase attenuation constant. Okay, so we start with this basic formulation. Well, for the time being, we'll just focus on the amplitude variations. Okay, we'll just focus on the. That's what really matters, because that's going to reduce the signal strength. Variations are not so. Okay, so we'll just pick without loss of generality, we'll stick with E equal to E naught. E raised to minus alpha okay. Now what we could say is that this is free space and there are n obstructions. The signal leaving each obstruction goes through attenuation of power of minus J delta e to the power of minus alpha e to the power of minus alpha I multiplied by delta Ri, because that is the thickness of the obstruction. Okay. The thickness of the. So if it goes through a number of obstructions, after leaving n obstructions, you can write the net field En as E naught e raised to minus alpha I delta Ri I equal to 1 to n. Why is it summation? Product of signal here signal here multiplied by e raised to minus alpha 2, then we will get a summation. I equal to 1 to n. We are just arbitrarily choosing n obstruction. We don't really know what is characteristics. Delta R and alpha is. We don't really know. There are obstructions. Okay. Now we call this entire right raise it as e raised to e naught, e raised to x, where x equal to this is what we really need to focus here. The alphas and delta Ri's vary from obstruction to obstruction, and they vary randomly because we can't really say much about these obstructions. They have no vary randomly from when you know very little about summation of large sequence of numbers, something that comes to very handy describing the behavior of x. All are modeled as random quantities. Okay? Limit as n tends to infinity. By central limit theorem, sum of infinite number of random variables. Okay, we don't know the distributions. Infinite number of random variables. Up with x, which has normal distribution, some mean. Get the mean and variance, well, we can only measure it. Okay, what we can observe and measure is x. You can't possibly measure alpha and delta x. That's not going to be easy. Unless you go through electromagnetic entire surroundings using. That's a little bit hard, although some people attempt to do that. Another approach that we can choose is central limit theorem, model x as it. Okay? If that is the case, as n tends to infinity, applying to central limit theorem. Not familiar with this? Probability density function of x the probability density function of x is written as p of x. For simplicity, we don't put capital. Take it as 1 over 2 pi sigma x e raised to minus half x minus mx square divided by like I said, mean and variance one has to calculate. For example, in later exercises you will see that if somebody has given you a pathless using Hata's formula. Hata's formula gives you the power level, and power you can get the voltage, right? And voltage get the voltage exponent, sort of figure out value okay. That y is equal to En by what is the distribution of capital Y? Capital Y. Same distribution of X except that the mean shifts by some. So just scale the random variable, right? Okay. So Y has normal distribution. Small y has e raised to x. You have to find the distribution of x. So you have to find the distribution of. So what you call as what we call log normal distribution. The logarithm of it has a normal distribution. Logarithm of small y has normal distribution. Therefore, y has set you have log normal distribution. That you can figure out. Okay. Usually we work with the logarithmic quantity because whether you're interested in power or voltage, well, the electric field is related to the voltage, right? Electric field is related to the voltage, and if you square it, it is related to the power, and you take the logarithm of it, okay, and you end up with still x multiplied by some other constant, right? Doesn't matter whether you square it or not. Only voltage you have this. If it is power, you have a factor 2. It's going to be squared. That appears as a factor 2. Nevertheless, voltage and power, take it in logarithmic domain. The distribution is still okay. So, if you want the mean value of y, it's already in logarithmic domain. You can take any base and you can put 10 log 10 or 10 log 10. It is 20 log it is power, if it is 10 log it is. Okay. So the bottom line is here, if I just take the voltage is described here, if I take 10 log base 10, where it becomes. Okay, the point here is make a measurement on the power, and if you know the mean power, let's say that mean is given by the Hardas formula. Hardas formula gives you take that power and consider it as a mean power for this process. All you have to compute is, all you have to specify is the variance. Of course, you can't say that Hardas formula strictly gives you the accurate mean power. If you want to know the mean power, you must better measure. But in modeling, we use the Hardas formula to get the power level, that is the mean power level. And then, usually we prescribe a variance for this process, which is on the order of dB is the variance for power. Where this and then okay. Variance is so what do you learn from this? Variance of the power, signal power is a log normal random variable. Of course, the power described in dB is a 10 log PR is normal with mean some mean and variance the mean P and variance sigma. This is normal random variable with mean P, and P is in what? P is in and some variance sigma square. Sigma square is typically in the range of 6 to 80 or 5. Now this valid measurements have been carried out and variance has been found to be in this range, and the received signal power, you take these measurements and find out the distribution, and it's log normal, or in decibels it is normal is written as 10 and brackets mean comma variance. So to model a system, what we can possibly do is this P, the received signal power in decibels, it can be computed from Hardas formula directly. That gives the mean at that location, and you can add an additional or add or subtract an additional power. If I ask you to simulate a log, model the received signal power using a log normal, Take the Hatta's formula or any other formula. Calculate the mean power at that point. Right? Generate a Gaussian random variable with that mean. Generate a random variable. Okay, an instance of power. Once you know the received power, then you can model statistically modeling. Because in real life, you take what you get. You measure something that's way of describing systems. Also, when I put a base station and somebody asks, what is your coverage? No, because at the edge of the cell, at the 2 km point, your signal to noise ratio, noise level is fixed, signal power is fluctuating with log normal distribution. So it can be high or low. So now you can only describe the coverage statistically. I can say we can get coverage 95% of time and SNR of at least 10 dB SNR or some power receiver signal power level at least 95%. Directly affects coverage calculation. In other words, 5% of the time. Anywhere in the cell, you can still have outings. That is, you don't meet the target SNR. You can already see from a deterministic world, we quickly moved into describing everything statistically. Makes sense, right? When you make a call, there are no guarantees that it will always work. Well, there are so many things that are. No, we'll come to those things. This is, we're not come to that. This is only passing through these obstructions. That's all. Obstructions are not causing any delay as such. Yeah, but phase variation will not attenuate the signal. Put that, you will have sum of several betas, right? Just another beta, and that will be yet another case. Okay, this is the most crucial one, right? Attenuation is what we are most interested in. But phase variation also, well, it just becomes probably at another random phase. Okay, but we'll come to the short-term modeling where we also pay attention to the phase. Okay, fine or any other doubt? We'll come to the time part of it. So I have presented the notion of shadowing, which is caused by unknown obstructions, and it is said to have the log normal distribution and the power variance of 6 to 8 dB. And you may wonder what the mean value is. Well, the mean can only be found by again measuring the mean value at that point. Variance can also be found by measuring the variance at that point, but you can't just go and make measurements everywhere. So general rule of thumb is the variance is on the order of 6 to 8 dB. Is it? Calculating the average power in Ada's formula. Ada's formula is very similar to the free space formula in spirit. There is just an expression for PR, and you just find it, and that is your power at that point. And that power, we take it as a mean power for this process. The Ada's formula gives you the power at a given distance d. 1 point. Distance d, that is a power. Of course, you may say, let's take a transmitter and I measure the power here d and I measure the power at all these points. They will be equal if you go and measure them. All those points, if you go and measure them, they need not be equal. Why? But the obstructions that they go through in different directions can be different, unless it is. Okay, so one may wonder, what is the statistical description of all the powers measured here? What do you think it could be? Well, we are claiming it to be log normal. The mean, well, the mean is the same for all the points, but still you will exhibit variations. The variance is 6 dB. Draw points in a normal distribution. It's as if you're drawing points from a normal. Of course, we're not doing that physically. They're just power measured there. But if you have to model something in a computer, what would you do? Take the received power, compute from Ada's formula, and you just draw a random number, the mean and variance. If you want to model the entire area, okay, at each point, the d is different. Okay, at each point, the d is different. And then, excuse me. Let's talk about the points here, right? How do you model the signal at those points? Okay, let's say you want to simulate it. Well, you know the mean at each point, but you can't possibly draw a random number for points that are too close, because there will be correlations. If there are 2 points which are, let us say, 1 meter apart, and here and there, perhaps the average power signal strength will be pretty much the same, because these 2 points are very close from the perspective of this. Somewhere here, and the signal is transmitted. If the points are, let's say, too close, then the average signal strength, you can assume it to be pretty much the same. So, if you want to model this, you model them as every 50 meters, you create these circles with every 50 meters, let's say, all the points here will get same power, but from circle to circle, you draw a different, of course, it's a model, of course, it's not physical reality. The assumption here is that every 50 meters, these random variables decorrelate. Otherwise, you have to create a model where you introduce correlations as a function of r and theta from this origin. Okay, so we don't want to complicate matters so much. What we do is, if you want to simulate this a communication system, you put one transmitter, you draw a circle, let us say, and you want to measure the signal power at various points. You take a decorrelation distance of, let us say, 50 meters, and we assume that every 50 meters you will see a different number. Or you can create a model where you can in fact introduce correlation between this and this. If you are not comfortable with that complete decorrelation, if you think that 50 meters is too close, then we can kind of correlate these 2 points using you can create correlated random. Variables. Okay? So that will come to when you actually model this. Point is, so we didn't talk about actual correlation between different points in space, but if you take points sufficiently far apart, they will be statistically independent. Just Points of a difference. No, we're not talking about reflections here. It's a single path, it's going through many obstructions. Single path. We're not adding many paths. That's what I'm saying. We're not really introducing even the time axis here. Signal transmitter and receiver. Okay. It's going through these attenuations, but they're not introducing delays in the signal. They're not introducing delays because this thickness is too small to introduce. Okay? So we're not introducing Doppler shape, we're not introducing short term fading, we're not introducing those impairments. What we're introducing here is effect of a signal passing through a number of obstructions. Then we'll come up with another model when there are reflections and around because of all these various in inner and around. If there are many reflections, then we have to add up the signal. The signal which you get because there is reflections in there. And you will match these two. We don't well, we are modeling them as independent. The obstructions are physically different always. That's what I'm saying. Take another point arbitrarily close to this. Traversing through obstructions, they share the same common obstructions. When we go there, these obstructions could be quite different. Of course, you may say in the vicinity they may share the same obstructions always. There are always some correlation with them. Okay? So you have to create a model to introduce this. See the point? There is always some common obstruction they may share at the base station. If there is one big reflector somewhere here, all may. Okay? So essentially, the signal strength is always correlated in time and space. Signal strength, time and space. But we are only talking about space here. But we are talking about the correlations in time. Sometimes you can interchange the correlations in time and space. Like saying, move here, get correlated fading, of course, in short term. But then by the time you have moved there, it's like you can take it as another point in. Come to that a bit later. So just let's stick to this bare simple model where the random orthogonal distribution. Like we said, it is the thickness of this obstruction. Anything, a building, it's a wall. It could be a tree. If it is wall or ignore them. I'm saying this is model those things as well. There is a wall, there is a path that goes through, right? Let's focus on that path. Not going to look at the energy that is diffracted and reflected. The wall, and if it's reflected, maybe it will go backwards. We don't care about it. Okay? If there is solid obstruction, there is something that goes back and something that grazes off surface, but we are interested in something that goes. Let it go through all the way to the receiver. And we'll just model these. Of course, this is a very hypothetical model in a way, but it does give you some insight into what could possibly happen. It does go through so many obstructions. Validate this. Okay? You may have two obstructions, you may have one. If you have one or two, then obviously this won't hold because we are talking about infinite number here. So you need 5 or 6 obstructions. Okay? Alright, so let's move on. Okay, now we have to answer this question. What about time variations? Right? That is very important to us. No notion of time here. We're just talking about the attenuation. Okay. So let's say this is the distance d from the transmitter. Okay. And if there was no variations whatsoever, the power could be decaying like this. Okay. Power could be decaying like this. Linear because we're probably measuring in decibels. Okay. Power in decibels. Why is that linear? Over d raised to alpha, and if you take 10 logarithm, the relationship is linear with the slope of the scale. Okay? Okay. If there is shadow fading, you might observe something like this. Shadow fading is the log normal fading. Use this notion. Shadow fading and log normal fading in thing. They imply the same. Shadowing because log normal fading. Sometimes we also call long term fading. Okay. So these are basically the signal strength measured in decibels. This is probably a real, maybe the measurement may look like this. But then you may say, what is the shadowing here? Well, the deviation from this is the caused by the, that is the randomness. Deviation here is different from the deviation here and here at different distance. But you can see, but still there is some correlation because it changes smoothly. Cannot take out change. Okay. Now we also have variations around this. Variations plotted as a function of distance or time. Why is distance and time are interchangeable? Are they? So from here to here, it will elapse an amount of t time. So the distance and time, right? Of course, we are moving away from the, traveling away from the base station along a straight line. Time are interchangeable if you are moving with a constant. Isn't it? Yes, we said so. It's correlated, but at some point it becomes independent. Mean also changes distance. No, the mean is a function of the distance because the path loss is determined by d. Clearly a function of distance. Too close, then it won't change. Obviously, if they're too close, you'll get the same mean. It doesn't change. Correlation between them, we have to. Anyway, let's ignore that. Talk about log normal fading or shadowing or long term fading. But then, as you move along, within a move even a few inches or centimeters, you will observe a rapid change in the signal. Imagine you move few inches or centimeters, or on the time axis it's a few milliseconds or tens of milliseconds. How are they related? What's the formula? Huh? So V being constant, I can put either V or T. Right line maybe. Huh? What is it? Velocity of the user, the rate at which you are running or moving or driving in a vehicle. No, it's not the velocity of signal. It's not the speed at which, it's not the electromagnetic speed. That's the speed of light. This is the speed of the user. That's the speed at which is moving. The mobile speed. Mobile velocity. Well, hypothetically it is same. So in the short term, the graph is the same. If you take a short segment, if you interchange D and T, think about it. And here, I move a little here, just what fraction of a, and I will get a completely different signal. But their mean values are the same. See, the local mean is, what is the local mean? That is the local mean, that doesn't change. But here it is 1 and it could be 10, a few centimeters up. Come to this. This is called short-term fading. Well, how do you think you get diversity among antennas? The antennas are placed only lambda by 2 or lambda apart, or even 10 lambda apart. But it is like signals may be statistically independent. It's like saying you're moving with an equivalent velocity from here to get the same. You're moving within a few milliseconds, you'll get a different state. That effect is quite similar. Okay, we'll come to this later. Let's go through the mathematical model for this short-term fading and what is the rationale for this. Okay. We have a transmitter somewhere here and there is a receiver at some distance. Okay. Well, first of all, this receiver is not moving. First, we'll develop the model for the case when the receiver is not moving. In other words, if I stay here, I get one measurement. Okay. And what is the statistical description of that measurement? Okay. Assume that the receiver is not moving. Then we will introduce. Here is very important for you to understand. It will take some time to sink it in. Let's consider the case where. So let's assume that there is no direct line of sight between them. Okay, but all we get is reflections from the surroundings. Okay. Essentially, there is a set of local scatterers. The wave impinges on it, and then something causes this to fall. A part of it goes here, a part of it goes here, and the part reaches receiver, and the receiver receives lots of rays because of different obstructions in its vicinity. Obstructions in its vicinity. Of course, these are not proportional. Usually, it should be. Therefore, this path is kind of common to this. So, if I have to draw it differently, scatterers are here. Pretty much goes through it. So, these all go through the same obstructions in a way. Of course, we ignore the scatterers at the base station side. Okay, let's ignore them for the time being. And then take the scatterers only in the vicinity of mobile station. And all of them go through more or less the same kind of shortening phenomenon. Okay? But here, they go through signal received is bounced back from any. Okay. That is the case. You can write the channel impulse response between the transmitter and receiver as so each path contributes to an amplitude gain AI. I mean, I'm talking about the path that is received here. It has amplitude AI and it comes with a delay Ti because they travel different distances before it reaches the destination. But Ti's are very small though. They're all comparable in some way. They're in the very close to each other. Okay. Now we're going to transmit a signal S of t, a single tone. And we're not going to introduce modulation here for the time being. A e to the power of j omega naught t, omega naught equal to 2 pi f, where f is the carrier frequency. That is usually on the order of 800 megahertz, 1 gigahertz in the range. Talking about a carrier transmitted frequency fc, the transmit signal. Now we want to see how it will be received. Okay? So the y of t received signal is the convolution between s of t and h of t, that is a is that right? I wrote the expression for h of t and I convert this with e to the power of j omega naught t, and that ends up being, what is this? Huh? E to the power of j? Huh? T minus T. This is y of t. Then I'll take out a e to the power of j omega naught t okay. Okay. The original transmitted signal, and what is this? That is not something you wanted, right? This is the undesirable part. transmitted something, but you got an extra term which is the sum of n terms. Okay. Now the question is, what are these A's and B's? Yeah, A's are the attenuation factors created by the local attenuators, not these something in between. That part we left out. We assume that there is no attenuation in this range, but later on we'll make some. This is the local attenuation. And omega naught Ti can be written as theta I, because Ti is very small usually, and omega naught is generally very large number. Okay. Therefore, whole thing can be modeled as, that's really of interest to us, right? The single part you can take it out because anyway it's known. A e to the power e to the j omega naught t. Safely you can take A to the 1 and this is known because the center known segment. Of this system. Not the impulse response, rather the after going through this. It's sort of like a very narrow band system. So you're sending a single tone of bit. Single tone, it's a bit 0. So it's like a very narrow band system. So this model is applicable to sending a single tone. We're not talking about a broadband system. The characteristics for a broadband system are quite different. We're talking about a very narrow band system. We're singing a single tone, 0 bit, and we get no pulse here. Single tone continuous. Talk about sending a pulse also. Okay, so what we want to do is we want to characterize this part. Unfortunately, we don't really know anything about tau i's and A's. Because the local scatterers are not known to us. Whenever you deal with something that is not known to you, one way to handle it is to use text. Okay? So, this part, we call it R e to the power of j theta, that is equal to summation I equal to 1 to n ai e to the power of j theta I. And that is equal to x plus jy, if you write R e to the power of j theta, that, and x is equal to ai cos theta I equal to 1 to n y equal to ai sin theta I equal to 1 to is the r square equal to x square plus y square, and x equal to r cos theta, y equal to r sin theta. as n tends to infinity, this approaches a complex Gaussian distribution. That means x and y approach independent real Gaussian distributions because we have an infinite sum of infinite number of complex random variables. In this case, we have a sum of infinite number of real random variables. This approaches a real Gaussian distribution with some mean and variance. This approaches a real Gaussian distribution with some other mean. But it turns out that they are identical distributions. They're statistically independent. The mean for x. Okay. Limiting case as n tends to infinity. Complex Gaussian distribution. The central limit theorem with expected value of x equal to expected value of y equal to 0. Sigma x square equal to okay. But then what is the density for x and y? Let's say the density for x is p of x is equal to 1 over square root 2 pi x e to the power of minus x square divided by 2 sigma x square, and p of y also has form. And sigma x square equal to sigma okay. What about the density of r and theta? I'll leave it as homework exercise. Find the density of r and theta. Find the density of x and y. Find the density of joint density of p r theta and into marginal density also. Find p r theta and find p r and p theta, which are the marginal densities. For x and y, you should be able to. So r is the envelope of the signal. Is the voltage, right? That is equal to square root of x square plus y square. And theta is a phase and it has its own distribution. How to find it? Submit in the next class. Okay, now the question is, what if you have both long-term and short-term fade? What happens? Y would be R, and talking about baseband modeling, okay? R is equal to J theta. Make sense? P is called PR. PR is mean P and variance. Does it make sense, this model? Just look at it and tell me whether it makes sense. Sigma x square and sigma y square. What is the total variance? Sigma x square plus sigma y square. That variance mean of the log normal shorter. This variance, the power contained in the signal, remember it is squared around long-term power. So the mean of this short-term fading is the variance of the short-term fading is the mean of long-term fading. What does it really mean? What it means is that transmit something, it goes through shadows, you get some voltage, and again it goes through local reflections. But presume that all these local reflections have already gone through the same long-term loss they are subjected to. Then they again go through local reflections, and that manifests as R. Simulations, what we do is, a convenient way to do this is, PR is normal mean and P and variance sigma square. This comes from Harda's formula, and you make sure that this process has unit power. So that sigma x square, sigma y square, that is the total power is R square, right? Expected value of R square is equal to expected value of sigma x square, sigma y square. We make sure it is 1. This is a way of modeling. You can also model it as, you can bring this into this and you make this PR. You make expected value of sigma x bar, I will say, not x bar. I change this, right? Otherwise, you can write expected value of R square equal to expected value of sigma x square plus expected value of sigma y square, that is equal to the mean, which is P, or whatever you may call it. That comes from, this is power, right? This is the local average power of the signal, and that local average power itself is a random variable because of shadowing conditioned on That's one way of looking at it. Sigma x square plus sigma x square is the local power, but that power, if there are no obstructions, it would have been constant. But there were so many obstructions, and the obstructions are common for all the signals that have been, all these signals, the long-term obstructions, are assumed to be same. If that is the same, it just comes out as a multiplicative factor. And that manifests as a variance for this process because you're multiplying with something. About it. So if I have asked you to simulate, model the system, that's how you would model it in baseband. The baseband modeling of system. I have omitted e to the power j omega naught t there. That is not of relevance. But again, there is no Doppler in this system. I have to introduce Doppler. Okay. There is one more little topic. I'll just briefly mention it before we close this. Okay. What if there is no what if there is no shadowing, but there is a strict line of sight? Oh no, it's not like this. What if there is a complete line of sight and unobstructed component? In addition to that, there is local scatter. We write it mathematically. That means there is a lot of rich scattering locally, but at the same time there is a strict line of sight component which is not going through this local scatter. Where we write it is S of t or e to the power of j theta, e to the power of j omega naught t, this is what we had written before, plus a times or some constant a times capital A times e to the power of j omega naught t. This is the line of sight component. This is the scattered wave. Total is what is received. So if I rearrange this, I can write it as x plus a plus jy. Can I write like this? Is that okay? X is the real part of the process, short-term process. Then I can add capital A to it because it's like A. What this means is you have a direct line of sight to the base station, no obstructions in between, and then there are trees around you, but they are still going to give you some local reflections. Then you have a line of sight component plus all the reflected energy from the surrounding. So what is the variance of this x square plus sigma y square? Well, that has to be specific. It has to be the base station directly, and it has not gone through any obstruction. So you have A to the power of omega naught t. Of course, you have to put a delay there. We know it. Then there is other part which is just collected from the local obstructions. This is possible, right? In the other case, the line of sight is strictly not there. Everything is collected from the another scenario. We call Rayleigh fading, and the density function for the envelope of the signal in this case is pretty common. Okay? You have to find the density for the envelope. You have to find the density for x plus a square plus very called Rayleigh fading. Line of sight. No, it is line of sight. You can. The only thing that can change is you can get it from free space formula from line of sight. A is a constant. Okay, we will not work with this density functions here. But in the previous case, you must go through the derivations because they are very important. Okay, in the previous case, R is known to have Rayleigh distribution. Theta is known to have uniform distribution. But you will have to derive it. R has Rayleigh density. And theta has uniform and uniformly distribute over 0 and okay, we'll stop here today. So just drop all the homeworks in my office, or if you want to send it by email, that's also fine. Grab this, show it in the next. Who has not been able to complete the previous